Oh, yeah. Number 12?
Yeah.
Part E. Oh, yeah. Okay, so. And you're trying to find the GCF. Okay. So, like, guys, one approach to finding the GCF was to break it all the way down, right? So, for example, if I had to find the GCF, 24 and 40. How would you break 24 down?
6 and 4.
6 times 4, I love it.
3 and 2.
3 times 2 and 2 and 2. So 3 times 2 cubed, and then 40.
4 and 10.
4 times 10, I love it.
And then 2 and
2
2.
times 2 times
5,
2 times 5, right?
Prime factorization.
So 2 cubed times 5. So here's the funny thing. I mean, that problem looks difficult to you, but they've actually done a lot of the work for you. What's the GCF? Can you tell? How many what's do they have in common? What do they have in common?
2, 2.
How many?
2, 3.
3.
Is that 3?
Right? Yes, maybe?
Yes.
All right, so do you understand what I'm trying to say? They've already done some of the work. They broke down whatever the number used to be. They already broke it down for you. So let's make a harder example, but still it's not going to be that crazy. So these two numbers. All right. I like it. What would the GCF be between those two? How many 3's do they have in common? 4. How many 7's do they have in common? 2. So remember the shortcut was take the smaller power. 5 to 28. I like it. Now if you needed to, if they ask you to, I don't think they do, you can multiply all the crap together and see what that number is. But it's actually great because they've already done the work. At least the first step. Right. Is that, so that's all right, right? Okay.
Yeah.
I think there's 2 other problems like that, right? Okay. Yeah, buddy. So you just got to be careful where they put the commas, so you know how many numbers they're talking about. So that was number 12 in 5.2a. It's sort of like this. This is kind of the idea, and then this is what number 12, 5.2a looks like. Let me put like number 12. Yeah.
Do you want the GCF in that form, or in like the actual number form?
Oh, that's what I was just saying. It didn't really say, so I'd take it either way. In fact, since they gave it to me in one way, I'm going to give it to them the same way.
Question.
Yes. Yes.
I was gonna go ask, can we work on the quiz?
Yeah, I'm taking questions right now. We could do that. Let me take our question, and you get your question right.
Thank you.
Yeah. It's crazy. Yes.
Set A 5.2 number 20.
I love this. 5.2a? 20? All right, this one says, 2 numbers are said to be betrothed. Do you guys know the word betrothed? Okay. Some of you guys do? What's betrothed mean? Yes, they're going to be married. They're betrothed to each other. If the sum of all proper factors greater than 1 of... Okay, let's get this figured out. So they are considered to be betrothed if... Get in there. The sum of all proper factors greater than 1 of one number Anybody remember what proper factor means? Anybody? Proper factor? All the factors that aren't the number itself. Like the proper factors of 9 are 1 and 3. Okay. Okay. If the sum of all proper factors greater than 1 of one number equals the other and vice versa. Okay. Get in there. Become a word. All right. And vice versa. I like it. Cool. So they give us an example, think of, right? 48 and 75 are betrothed. 48 and 75. What are the factors of 75? Let's see. There's 1. What else goes into 75? What's 7 plus 5? I'm just listening to the factors of 75, correct? That's all I'm doing. So what goes into 75? 7 plus 5 is 12. So what else goes into 75?
5.
True, but that's true. But 7 plus 5 is 12, therefore what else goes in? 3, because it's a factor of 12. What else? 6 doesn't work, 7 doesn't work, 8 doesn't work. Square root of 75 is like 8 point something, so that's pretty much the turnaround point. So then I can say 5 times 25, 25. 5 times 15 is 75. And 3 times what is 75? 3 what makes 75 cents? 25 cents, okay. And then 75, but 75 is not a proper factor. So sum of all proper factors, okay, so I can eliminate 75. Is that cool? Because a proper factor means all the factors that aren't the number itself. Greater than 1, all right, let me eliminate 1. So what is the sum of all the factors that I've got left here? What do you get when you add all these together? So what do you want to add those together? 48, yeah, so that equals that. All right, so real quick, I want to make sure you understand the idea behind this weird-ass word, right? Betrothed. Just to let you in on a little secret, I had never heard of this before, to be honest. I mean, my God, I had never heard of this idea. But for two numbers to be betrothed, the sum of all the proper factors of one must equal the other one, and vice versa. So 48, if you break it down, and you do the same thing, they should add up to be 75. I don't know if the book shows you that happening. Okay. So all you have to do, so the biggest problem with this exercise is factoring. They give you bigger numbers, of course, because it's a math book. And math books are like math teachers were all evil. So they give you a harder problem than what the example was. But the biggest problem is going to be just getting all the factors figured out. Is that all right? Who asked that question? Oh, well, no, you did. You did.
Yeah.
Okay. So, like, for example, part A has got the two numbers 140 and 190. 195, yeah. Do you guys remember? All right. Do you guys remember the method to see how long this list should be? You guys remember we talked about that? To figure out how long this list should be? So like if I take 140 and I break it down, who remembers what to do to see how long that list should be? Yeah.
Don't you add 1 to the exponents?
Add 1 to the exponents, I love it. So this will be 3, this will be 2, this will be 2, right? Because there's 1's right there right now.
And then you multiply?
and then you multiply. So I expect the list of factors for this to have 12 things in it, right? So you got like 1 and 140 are kind of the gimmies, right? 2, and we can do like that girl in the video. Weehaw. 2 and 70. Weehaw. All right, you guys kind of with me? So you can, to me, factoring is relatively easy, but it's also really easy to forget a pair, right? Especially like if I said factor 60, does 4 times 15 come to your brain when I say factor 60? Probably not. Not to me either. Well, now it does because I'm used to it, but, right? So our brains aren't going to pick up some freaky little things, but at least if I go, all right, I know there's supposed to be 12, so if I get all the ones I can think of and there's not 12 of them, I got to slow down, figure out what did I miss. So I think that's going to be the hardest part. Because once you get all these done, you're going to take all of these, not this one, because that's not a proper factor, and not this one, because it's supposed to be greater than 1. And if you add all of these in the middle, it has to equal the other dude. That's all it means. So again, I think the hardest part's going to be not missing any factors. Andrea?
I've experienced with that in the book in what is it, 6.1 and 5.2.
Yeah. Yeah.
Oh, and I have 2 questions. One is from the test, from test 2, and the other one from the problem of 6.1, set B, number 24.
All right, let's see. So this is on page 223. Oh, okay. I love this question. All right. We're going to look at something related to this question today. It says, let's see which one. Where'd it go? What was it again?
24.
24. Okay, so 61B24. So if you take, if the same number is added to the top and bottom, are you generally allowed to do that? Does that create an equivalent fraction if I add the same thing to the top and bottom of a fraction? So for example, somebody give me a fraction.
4.5.
Say it again?
4.5.
Oh, okay. Thanks for that. If I add 2 to the top and the bottom, I get 3/4. Is that the same? Hell no. I like it. But the question is, if you do that, understanding that the new fraction really has nothing to do with the original fraction, is your answer going to be greater than, less than, or equal to the original fraction? Justify your answer. So they want you to look at it. We could have just picked, now in this case, was our answer bigger, smaller, or equal to the original?
Greater.
Yeah. Now, we could have just picked, Luis could have just picked a fraction that happened to come out that way. So you got to try a few more.
How about 2/4?
Well, that's the same as 1/2.
3/6?
Same as 1/2. Right? Don't they all reduce?
5/8.
So 5/8. I love it. And you can change, I added 2. But they just said add the same number. So you can add whatever. Give me a number to add 5. So if I add 5, I get 10/13.
That's still greater.
How do you know?
Because we know that 10 is bigger than 5 and then 8/3. But if you're looking at decimal points.
Yeah, we're not looking at decimal points yet. We don't know decimals yet. So who remembers how to check to see how 2 fractions compare? Which one's bigger?
From the denominator.
So now, this is what we did. That's how we got the 2. If I do 13 times 5, what's that? 65? And if I do 8 times 10, I'll do that one. Okay. Which one's bigger?
The 80.
This one. And that same thing would go between these. So as long as you bring this up here and that up there, the sign you use here is the same sign that goes here. So again, that did come out bigger. Now, twice as much evidence as we had, it kind of feels like this might be just a true thing, right?
Yeah.
Okay, so now you gotta maybe do a couple more examples, kind of try to figure out, is there a way to explain why this might be true? But at least I want everybody to understand what they're trying to say.
So, can I just say the fraction is greater than if it keeps going like that? Or is there a way?
Well,
that
that's
make-
good evidence, but it would be neat if somebody could figure out how to prove it. There's actually a way to prove this, but you might imagine it's not going to be like a pretty thing to look at. Well, I think it would be pretty, but anyway, just depending on your point of view.
Okay, now I have a question about the test 2.
Sure.
On 1C, I have the original worksheet right here.
They got one. No, that's test 1. What's that say?
On 1C,
Here we
it says 39 times 59. It says find the following.
Oh, yeah.
Distinct strategies.
So, this is the one, so we're kind of used to something like, if I said, what's 50 times 29, which I know is not the problem. What could I do to kind of mess with this so I can make this easier to do in my head? Yes?
50 times 30.
50 times, well, that won't be the right answer.
20 plus 1. 29 plus 1. Right? So 30 minus 1.
Does that make sense? Because 30 minus 1 is 29. So then 50 times 30 is relatively easy. 50 times 1 is nice and easy. Are you with me? Now, what did I do? Oh, I lived up to my math teacher position. And I said, I ain't going to give you any nice whole number. So I gave you, what was it, 39 times 59. But can't you just do this? Can't you just do this for both of them?
Yeah, so
Yeah.
it could be 39 or 40. So 40 minus.
What is 39? 40 minus?
40 minus 60? No, 40 minus 1.
Right? And then 59 is what whole number minus something? It's close to 59 is
60
close to 60, and 59 is 60 minus
minus 1.
1. Okay.
And
And then you can just do. Right. Yep. There's an actual, not necessarily a practical application, to be honest, but still is an application of foiling, right? Do you guys call it that, foiling, when he did repeated distribution between 2? Oh boy, you guys doing right?
Bringing the
Remember this stuff here? When he did like x plus 5 times x minus 7? And does this ring a bell at all?
My teacher called it the rainbow method.
I like it. I like that better.
So that has to be something I use mentally computive.
Yeah,
right?
totally.
Okay.
So 40 times 60, I really want anything, any whole number multiplied has got to be easy. 4 times 6 is 24. 1, 2 zeros. Right, and then you just got minus 60 minus 40, right? Minus 60
Negative 60.
minus 40,
Minus 40
and then plus 1.
plus 1. So 2, 4, 0,
Okay.
0, minus 60, minus 40.
Anything else, guys?
Plus 1.
Yeah,
Yeah.
good.
That would be, okay, that would be 3B.
Yeah, we talked about this a little bit. And I kind of love this idea. I mean, we all know, for example, that 4 times 5 is 20. That's amazing, right? So then a student, when they first learn exponents, might think 4 squared times 5 is 20 squared or something. Something like that. But of course, why is that not correct? Anybody? Why is that not correct? Yeah.
Because that's the 4 squared is at like 16.
True.
So 16 times 5.
True. So it won't equal 20 squared because 20 squared is way too big. But more in your face, there's only one 5. Right? So how can I make two 20s out of 1 5 and 2 4? I can't do that. Does that make sense? So if it was this, so this is not true. But if it was this, now how many 20s can I make out of 2 4s and 2 5s? 2 20s, yeah.
Then how
So, if I had this, for example, right? How many 20s can I make? How many complete 20s can I make? 2. And what do I have kind of left over? Yeah, I had 1 extra 4, right? So if you look at that problem,
but that's the thing. We had 3s, and then we had 2s,
I know.
and then 5s.
So up here I got 4s and 5s making 20s. On the paper I had 3s and 2s making 6s. Same problem.
So-
Exactly the same problem.
So what you did there was, so what's supposed to be is 3 times 2 is 6, but then we have 4, but then all that's left.
How many
over-
3s do you have?
We have 6. Well, 3, 4.
4 3s. And how many 2s do you have?
5.
5. 4 3s and 5 2s. How many 6s can you make? What do you need to make a 6? A 3 and a 2.
3
Stay with me.
2, that's
Right? 3 and a 2 makes 6 when you multiply. Right? So if I had 2 3s and 2 2s, I could make 2 6s.
Yeah, that'd be 4.
I love it. So do I have some extra something? Do I have an extra something?
You have an extra 2.
Beautiful. So how many 2s do I have besides that extra 2?
1, 5,
You got 5 total 2s.
and now we have
So you have
1.
an extra 2 and 4 2s, right?
Yeah.
So how many 6s can you make with 4 3s and 4 2s? How many 6s can you make with 4 3s
4,
and 4 2s? I really want, so 1 3 and 1 2 makes 1 6, yes?
Yes.
2 3s and 2 2s. I really want this to make sense. Watch.
3s. Yeah, I know that.
All right, so skip this middle shit and say 2 3s and 2 2s can make 2 6s. All right, I love it. So don't you have, you just told me you have 4 3s,
Yeah.
you have 4 2s, and an extra 2, right?
Yeah, an extra 2.
So how many 6s does this make?
At 6 4th.
6 to the 4th times 2. Is that what the student wrote down?
Yes, that's
Okay.
what the student wrote
All
down. So he would be correct.
Now you figure out how to put that together.
So yes, he would be correct because
You figure it out on your own time. Now you get that down on the paper. I like it. Anything else from homework or left over from the test or something? Yes.
24 on set A 5.2.
5.2 A24.
Yeah, 24.
Oh, now let's see. This looks something. Let's see. Did we talk about this one? No. Oh yeah, we did talk about this one. This is the perfect number one, right? Am I in the right place? 5.2 A24. The one about Euclid.
Oh,
That was where I think there was a typo in the problem. Let me see. Well, let's see if I can make this work. I got all this stuff up here to talk about here in a minute. I didn't want to move it out of the way. Lay it on top. Okay. So this one, I think the typo, they picked the wrong part. I'll show you what I mean in a minute.
so yes, he would.
There it is. All All right, so this one. You guys see that? Okay. Move it too much. So yeah, the typos, there's one typo. I think there were two things. Let's see, this one's definitely the wrong one. It should have been this. You with me? That's sort of an understandable typo. They're almost the same damn thing. But there's no way in hell this could be prime, except for n equal to 1 or 2. So that's not really interesting. So they meant to put that there. Let me see. I don't think there was another mistake. Yeah. And this is where you had to look. Oh yeah, this is where you had to look back at 13C, where they talk about what a perfect number is. Oh, scheisse. Oh, you guys are good. Okay. Oh yeah, that was the other typo. Where was the correct? Oh, here's perfect. It was 18. That's the other typo. 18C is where they talk about perfect. Let's see if I can do this. Do it. Okay, thank you. Oh man, I got so much crap all over the place. Yeah. So a number is perfect if the sum of its proper factors, that's the first time we saw that proper factors, is equal to the number. So you've got to find numbers that are in this form. Oh, scheisse. There we go. All right, everybody just stay there. Okay. Holy crap. You've got to find numbers that are in this form where this piece in the parentheses is prime, right? And where once you put this number together, the sum of its proper factors is equal to the number. So how the shit do you do that? Pick a number for n. So like, let n be 1. Looks like, right? Because 1 will make that a 0 power. What's 2 to the 0 power? 1. And what's 2 to the first power minus 1? 1. So you get 1 times 1 is 1, and that's not going to work, right? That's not going to do what it's supposed to do. Then you let n be 2. You see what that number is, right? Especially you want to pay attention to, if n is 2, is this prime? This piece right here, is it prime? 2 to the n minus 1, what's 2 squared? 4 minus 1?
3.
So that is prime. So then it's a candidate. So if you pick a letter, If you pick a number for n, and that piece is not prime, it's not even something I'm going to worry about because it doesn't follow what this says. And they tell you down here what n could be. I didn't even see they did that. That was kind of nice. So you can make a list of numbers to try by just changing n. Get a bunch of numbers, and then go back and look at perfect number and see if any of them do what you're supposed to do for the perfect numbers. You got to find the first 4. Okay. Now I almost don't want to say this, but don't do this. But I got to say it. I'll be really surprised if none of you Googled perfect numbers. List of perfect numbers. I mean, my God. If nobody tried that, I'm almost disappointed in you guys. But obviously, try not to do that until you got the answer, just to check yourself. Does that make sense? I mean, right? Okay. Yes?
Can we look at number 9 in the test? And
Oh, okay. So let me say this. Let's see, I'm not gonna be ready for you for a while. Get in. Let me remind you guys of one thing. Because basically everybody sort of didn't quite get that problem. That was the one about 2 goes into A, 6 goes into B, right?
yeah, and must 12, and then the must 12, and then the big line AB explain.
Now, I'm not going to say a word about this specifically, even though I just wrote it up there. Can somebody tell me if 5 divides X, what can you write down? What does that mean? Does anyone remember what I could write down based on that idea? So for example, give me a number 5 divides.
25.
25. What is it? Why does 5 divide 25?
Because 5, the last digit is 5.
I like it.
Because 5
Less
can go into
rule,
25.
more computational. Why does 5
5 is a
divide 25?
factor of 25.
Good, because
Yeah.
5 times
5
is 25. So if 5 divides x, that means that 5 times something is x. And I think we all did this when we put an m here. You guys remember that? No? Yes? If 5 divides something, that thing must be a multiple of 5. Does that make sense? Which kind of makes sense using the letter m. That means x is a multiple of 5. Can you do something similar here?
Well,
Can you do something similar here?
you can do something similar.
Totally.
There.
And then there's some cool shit you can do after that.
Like
So-
for example, can I do 2 dash 12?
So what would this look like? I'll do one thing with you.
2.
So what can I write? Since this is true, what does that mean I could write? If 2 divides A, then A must be, same idea we just had, right? 5 divides 25, so 25 had to be a multiple of 5. 2 divides A, so A must be,
4. Well, I said A
could
for
be,
12.
could be. Okay, love you guys so much. If 5 divides some number, I'm not going to tell you what the number is. Isn't that number have to equal 5 times something?
Yeah.
Okay. If 2 divides A, then A has to be 2 times something. All right, I like it. Can you write a similar thing for this?
Yes.
Can you then figure out what A times B is? Because you're going to have what A is and you're going to have what B is, right?
Mhm.
I love it. That's all I'm going to say. That's all I'm going to say. That is the correct way to prove this. When it almost sucks when something is true, because then it's harder to prove it. It's much harder much easier to disprove something. You just have to give me one instance where it's not true. Just one counterexample, I'm done. Right? Okay. You guys doing okay? Some of you guys look.
It's just that problem with number 9.
What's up?
It's just that problem with number 9. It was hard. At first I said yes.
Oh yeah, number 9 was freaky. I agree.
They said that I thought it was they both have a factorial of 2, and the prime factorization of 12 is using 2s, and 6 has 2s.
No, so you got too specific. You can't choose what A and B are. That's too specific, because it might only work for that case.
Oh.
You got to be completely general.
But how do we get completely general? That was-
Doing what I just said. So can you write something similar for this? Right? Same way we did this?
Well, you said 2m. You didn't really give us a number.
So when I say you were too specific, right? So what did you pick?
I picked A was 2. And
Why
then
did you
B-
pick A to be 2?
Because I figured that 2 divided by 2.
Sure. What else could it have been? Could it have been a different number?
12.
12. Could it have been 24?
Yes.
It could have been anything that was a multiple of 2.
And it could have been anything
No, wait.
with a multiple of
Wait.
6.
Isn't that what this says? Isn't this a multiple of 2? 2 times some whole number is a multiple of 2, right? Okay.
Sometimes it would be a multiple of 2. So like for say if I say 12,
That's too
Yes.
specific.
but that's the thing.
It's too specific. So, what can I write for this guy? If 6 divides B, I can write what? What must be true about B?
B equals to 6b. I mean to 6m.
Yeah, I can't use M again because it doesn't have to be the same multiple.
N.
So we normally use the next letter. Just like we use X and then we use Y. Because
But-
math people are not.
But then you said must 12 be multiplied of A
Yeah.
and N, and no.
Do we know what this is?
No.
Yes, we do.
Oh, well.
Because I know what A is.
It'll be M and N.
And I know what B is.
And it'll be
Stop. Don't I know what A is?
it's 2M.
And don't I know what b is?
It's 6n.
So what is a times b?
A times b is, that'll be 12mn.
All right, so I'm definitely not saying anymore.
2m times 6n.
Well, yeah, exactly, which is what she just said. 12mn. All right, so I'm gonna let you guys. We basically finished it. Now you just gotta take that last step. Yeah. Yes.
Kind of a general question about fractions. So when you try to figure out which one's bigger or not with the cross multiplication, and you get like one number, say it's like 1,156 or whatever. How do you know which number goes to which fraction?
Oh. Okay.
If-
So again,
does that make sense?
if I have any fraction and I'm comparing it to another fraction,
Yeah.
if I bring this up and I bring this up,
Mm-hmm.
whatever sign I put here is the exact same sign that
Okay.
goes there.
Thank you.
You're welcome.
What do I have to do for number 28 on 6.2? Yeah, 6.2b, number 28.
Oh, okay. Well, one thing is we haven't done 6.2 yet. We're about to get into it.
Oh, wait.
And the second thing is,
Oh, no, wait, I mean 6.1b.
oh, 6.1, okay.
My bad. I was reading the top of the blue thing.
You're fine. 6.1b, number 28.
Yeah.
Oh, okay. So tuition in public universities is about 2/9 of tuition at private universities, right? So tuition at public universities is 2/9 of private. If the average tuition at private universities is about $12,600 per year, where do you go? What should you expect to pay at a public university? Okay, so then you just have to replace this with what they told you. Now what's a little weird about that is, this is before we've officially talked about multiplication, so it's a little strange to put that here. Yeah, I guess they sort of can sneak it in because we talked about simplification, but it's a little bit weird to have that there, but oh well.
That would be 20,800.
Yeah, now you do the
I
work.
mean, 2,800.
Now you do the work, yeah. All you have to do is put here the number that they tell you that is.
Okay.
I like it.
And finally, this one was do I have to do number 32 after 28?
If I said to?
Yeah.
Wait, 32. There is no 32.
Just 6.1.
B?
Yeah, 6.1.
Okay. Oh, I see. Yeah, don't do that.
Okay, so skip 32.
We're not using their website, really,
Yeah, okay.
because I'm not going to make you pay the stupid amount of money to get access. Okay.
Okay, so then the only question I have left is 36.
Oh, all right. That one I'm going to let you think about. Are you okay? Oh, man. Maria just blew up. Okay. All right. All right, guys. Yeah, let's definitely get into this stuff now. So, 6.2, we start talking about adding fractions. We're going to start talking about doing things with fractions. One thing I want to start off with, why do fractions have to be so freaking hard, right? So let's talk about why that is. Why are whole numbers so easy and fractions so miserable, right? For most people. So one reason that's true is because most fractions are not really a part of a number system directly. So what do I mean by that? I mean, what is 0? I know we're not quite in decimals yet, but just go with me. What's 0.7 plus 0.2? 0.9. Why are we allowed to put them together? Well, because on one level, it's just what we do. They're both in the same place, so I can put them together like we have been doing, right? Does anyone know what fraction this is?
7 over 10.
Yeah, 7/10 because it's in the tenths place. 2/10, right? So if this is 0.9, then this obviously has to be 9/10. So any fraction that's over a multiple of 10, do we all agree finding LCD kicks ass for those, right? If one is 10 and the other one's 1,000, you're like, that's easy shit, right? They're always going to be pretty straightforward to get LCD. Why? Because they fall into our number system nice. Does a number like 1/12 fall nicely into our number system? No, we don't have any 12ths places because we're not using base 12, right? If we were using base 12, that would be easy. It would be 0.1. I don't know, that's a little too far. All right. Okay. So another big, so 1/12, general fractions like 3/8, 4/11 for damn sure, right? These things are nowhere near to falling into our base 10 number system. Okay, so that means that how we work with them will have to be fundamentally different than how we work with normal things like 30 plus 2 or something. Because aren't both 30 and 2, they're in our number system. So they have to be easy to work with. Okay. I really hope this is making sense. This is kind of interesting for me because these are ideas I've been tossing around myself that I've never gotten to teach, really, because I don't normally teach this, especially not since we got rid of Math 88. I used to teach it all the time. We had a Math 88 before. We had a Math 80 before. Good.
I thought you said 180.
Hmm?
I thought you said Math 180.
Yeah, we still have a Math 180, but we had a Math 80. Yeah.
What is that?
That was basically like computational math, not even algebra yet, right? Okay, so stuff like this, 4/7 plus 2/7. On the surface of that, that should be really straightforward without even understanding necessarily what over 7 means, right? Because we know what 4 things plus 2 things are. So 4 of these plus 2 of these is 6 of these. Whoop-de-doo. I almost don't even have to know what fractions mean to be able to do this kind of thing. I like it. So they only come into play when I start doing different denominators and talking about multiplication and stuff. That's definitely where you got to worry about what fractions really mean. So what if I had 3 20s plus 5 10s? And do we normally now this is like money, right? Are those like terms? Is that 8 anythings? Is that 8 30s? For example, does this equal 8 30s? Shit, no, right? Because they're not like terms. Yeah.
I just have a question. What's the name of this new section? Now it's 6.2, but like, is there a specific name?
Oh, combining fractions? What is that name? Blah, blah, blah. It just says fractions, addition, subtraction. Yeah. So this is where and then of course, remarkably enough, section 6.3 is going to be multiplying fractions. Yeah. All right. So what I really want you guys to get is 3 20s is how much money? $60. So isn't 3 20s 6 10s? Yes?
Uh-huh.
Could I now add these together?
Yes.
So how many 10s do I have?
11.
11 10s. I really don't know if you're getting the point I'm trying to make. We don't write numbers like this because there's no need to, right? Even when I'm trying to put money together, I'm not going to say 320, I'm going to say I got $60. Yes? I almost don't care that it's 3 20s, right? Maybe. But, go ahead.
I was going to say, how'd you get the 320s in the first place?
This is problem 2. Sorry. So this is what's given. So I got 3 20s, and you got 5 10s. So together we have the equivalent of 11 10s.
Oh, okay.
Yeah. So now watch this. This is sort of like, all right, this is not the exact same problem, let me be careful. So if I have 3/20ths plus 5/10ths, I still have that same, now, how did we do this problem? Didn't we make this into tens, so then we had like terms? So really, fundamentally, fractions, adding and subtracting fractions are based on like terms. Can I make these like terms? Of course I can.
Yeah, because they're both, because 20 is 10 is a factor of 20. So how about we multiply 5 and 10 by 2?
There you go, yeah. So LCD would be 20. By the way, real quick, I want to say this again. These are two different situations, right? One has no fractions, the other one has fractions. But I want you to see the parallel is, if we wrote 60 plus 50 as 3/20ths plus 5/10ths, we would have all the same problems that we have in fractions because they're not like terms. But when I write it like this, they're like terms because then it's 6/10ths and 5/10ths. Yes? All right, now, on one level, you're all like, of course that's the freaking way we do that shit. But to be honest, I've never talked to anybody about this versus this, right?
I prefer the fractions better because you're able to understand it more.
Well, yeah, fractions we worked somewhat with. This we haven't done, really. We don't do this kind of thing.
It just looks weird.
I know, it does
It
look
loves
weird.
Numbers.
Why would we do this shit when we could just do this, right? Yes? All right, trust me. I really want you to understand this middle shit, this middle stuff right here, you'll never see again, right? Because this is just me showing you what our normal non-fraction stuff would look like if I made it have the same problem that fractions have. That they're not like terms, right? So that is why fractions we have to treat them differently, but students don't like that because they think they're just numbers. They should work the same way, but they're not based on 10 all the time, in which case they're not going to fit into our number system neatly, so we got to have some other way to deal with them. Okay. So that's one thing I want to talk about.
So what would we do for after we get 3/20 and then we have 10 over 20? Can we add 10 and 3?
Say again, sorry?
What I did?
Yeah, of course. 3/20ths plus 10/20ths equals?
13/20.
I like. Again, just to make sure everybody, totally different problems, yes? One was fractions, one's not fractions, okay. That's one little weird thing I wanted to throw out there. It's always a little weird when you're a teacher and you throw something at people that you've never thrown at anybody before. And of course the response I got was sort of, so I don't know how it came off. All right. Now, what does, all right. Remember how we can visualize like 1/7 on a number line? How could we visualize 1/7? What would I do between 0 and 1? Split it into 7 sections. 11. 1, 2, 3, 4, 5, 6. So this would be 1, 2, 3, 4, 5, 6, 7 sevenths, right? So 1/7 would be right there. Pretend like that scale is good. So remember, we also talked about what this would mean. 4/7 would mean just 4 steps, 1/7 thick. Okay, I like it. Yeah, okay. So, how would I do, so what would this mean? Same way. What would that mean? Same way. So what does 4/7 mean? It means 4 steps of 1/7 each, right? So it end up 4/7 of the way to 1. So what does A over B mean? A steps of
B.
That would be AB. A steps of 1 over B, right? I love you guys. If I took A steps B big, that would be A times B, right? So if I divide 0 to 1, into B segments, A over B would be A of them. Take, do that A times. So it's like A steps of 1 over B. And again, not everything we do in here, well, this should be really obvious. Not everything we do in here is something you're going to show your students, right? We're doing a really deep dive into just certain ways to look at fractions, so that when you explain to your students the more basic stuff that we're going to do within a minute, you have a much better understanding yourself behind some of the stuff you're doing.
I don't think I'm gonna remember this.
But then, I mean, do you guys see the parallel here?
Yeah.
I mean, I could have done this with any number on the bottom. 1/12th, 1/800th, 1 whatever. And then any number on the top is that many steps of that. So A over B is A steps of 1 over B. So what's C over B? C steps of 1 over B. So what is A over B plus C over B? How many total steps of C over B, of 1 over B would that be? A plus C, exactly. A steps of 1 over B, and then another C steps of 1 over B, so it should be A plus C, and this is a freaking long-ass way to get to the fact that you're allowed to combine things that have like denominators already. But it's the idea behind it. You guys kind of with me?
Yes.
I know, this is, we know you can do that shit. I know you can do that shit. But have you ever seen the real explanation behind why you can do that shit? I don't know. Okay. Let's see, is it time for that? Yeah, we got that. So here is what I call the naive approach to adding unlike denominators. Some of you guys might have called this just the frickin' way I do it, Jeff, thank you very much, which is if I have A over B plus C over D, can somebody help me add those together? I want to actually add those together. Do you remember about the ice cream?
Yeah.
The two kids with the ice cream?
Well, I know how to do it with like normal numbers. I'm not sure what to say in this sense, but
Like this
try
one
to find
kid.
the LCD.
This one kid's got a B, and the other kid's got a
You
D.
want to add a D to the other side of the
Yeah, so he needs D, and what does this one need?
C. I mean B.
A B. All right, Blue, you're dead. I'm sorry, Blue. All right. You're just about as dead, Blue. All right. So isn't this going to be, what would that be then at the end?
AD plus BC over BD.
I like it. I like it. How would you, let me throw in, now, I call this the naive approach because are you always going to do this? Let me see if you guys remember. Would you do it here?
Yeah.
Totally. Because what's true about 5 and 7? What's that phrase
5.
I keep bringing up?
Prime.
Yes?
Prime.
Something prime?
Relatively.
Relatively prime, I like it. Now in this case, they're both prime, to be honest. Look out. So relatively prime means relative to each other, they have nothing in common. Okay. Luis, what's up? There you go. So whenever the two numbers on the bottom have nothing in common, you could just do that. You could just give this a 7, give that a 5. What do you do, right? So this would be 7 plus 15 over 7 times 5. Right, and then again, is that all right? You guys are okay? So again, what I did was I gave this a 7, a 5. And then you can't reduce that, so I'm done. All right. Now, of course, the bigger the bottoms get, the more you hope they have something in common, so you don't have to multiply by such a big-ass number and get these crazy-ass numbers. You want to try to get something lower to work with. Right? forgot where I was gonna go next. Damn, let me think. I was about to do something. What was it? I forget. All right, that's right. Let's see. I'm not gonna remember. It's okay. Now, real quick. Can somebody remind me? All right, let's see what you guys remember. Properties of whole numbers. Can somebody throw at me a property of whole numbers, like property of whole number addition? What's that?
Associative property?
I love it.
Is that
Associative. Somebody else.
Commutative?
Commutative. Somebody else. Another one.
The identity property is a zero.
Or you're still you, right? I was gonna make a joke about
What?
multiple personalities, but no. Right. So yeah. Okay. So we got associative, commutative, and what was the other one you just said?
Identity property.
Identity
plus
property.
Zero.
I love it. Distributive. This is not. I don't know if this is gonna help you.
Triangle.
Closure, I like it, right? When you add two whole numbers, it's still a whole number. So what about those? So we know those are true for whole numbers. We want to see if they're true for fractions, right? So what about closure? What do you think about
No.
closure under addition? If you add two fractions, does it still become a fraction? We just did it, didn't we? Is the answer there a fraction? In fact, what's really funny is we've been talking about fractions and we still haven't even defined what the hell a fraction is. Does somebody know what a fraction?
Ratio?
A ratio of what?
Numbers.
What kind of numbers?
Whole number.
Whole numbers, where the bottom is not.
Smaller than the top.
What can you not divide by? If you divide by it,
Zero?
you get a black
No.
hole. Zero.
Oh.
Right? Okay, another quick side stuff. Do you guys know why? I'm pretty sure I talked about this maybe on the first day. Do you guys remember why we can't divide by zero?
Undefined. But I don't remember anything else.
Well, that's a
I
big.
just
That's
remember
fine.
it's undefined.
So a little side note. Just remind you guys. What is 6 divided by 2? Holy shit. And why is 6 divided by 2 3? Because 3 times 2 is 6.
Oh, 6, yeah. I was saying 3 times 2, yeah.
Yes, with me? So 3 is the answer because it's the number that is defined in such a way that when you multiply by 2, you get 6. So what is 6 divided by 0? It would have to be the number that is defined in such a way so that when you multiply by 0, you get 6. Is there any number that's defined that way? No. That's why we call it undefined. I love it. Undefined. All right. This is definitely closed because A, B, C, and D are all whole numbers where the bottom's not 0. So therefore, this is a whole number still, and this is a whole number still, so it's still a fraction. It's still a whole number to a whole number, still a ratio of whole numbers. So fractions are closed under addition. Kind of makes sense. By the way, is 7 a fraction?
It could be.
Could be, I love it, because it's 7 over 1, or even 14 over
1, 2.
2, right? That's 7. I like it. So they're technically considered rational numbers, which is the more technical name for everything that can be written as a fraction. I love it. Okay.
Under addition.
Yeah, they're definitely closed under addition fractions. You get a fractional answer for any addition problem you do. What about commutativity? Commutative. What do I have to show for it to be commutative? I got to show that A over B plus C over D equals C over D plus A over B, right? Hello?
I just went to go get.
What's that?
I know, like I just went to go get water.
You guys kind of with me? Is that cool? That's what we got to show for it to be commutative, right? So we already know what this is, don't we? This is that, right? Is that cool?
Yes.
So this is this.
What does the one in the black ink have to relate to? The
What?
the right.
Oh, this. can't remember, I said something real quick up here. It's just what happens when you, this was related to something I had drawn here. Yeah,
Oh, okay.
yeah, it's on there. I gotta pull this stuff back. Let's see. All right. Oh man, this is so exciting. All right, let me see. Here, all right. This is pretty, this is what commutativity means, right? So we're trying to show this is true. Can somebody tell me what's true about what's AD and what's BC? What kind of things are those?
Variables, or multiplication.
Whole numbers. So in this whole problem, we're dealing with fractions, which are ratios of whole numbers. So every fraction I'm making is a fraction of whole numbers, right? What's true about whole numbers? Are they commutative?
Yes.
Yes. When you add? Yes. So isn't this equal to commute?
Same thing.
Which is what this is? Yes?
Yes.
Okay, so we proved it. Yay. One little, all right, so I am well aware this is not the most exciting stuff. I'm well aware of that. Well, one little thing I want you to realize is we've proven stuff with whole numbers. So when you go to start talking about fractions, you want to come back and use what we've proven already. It's not an automatic thing that fractions work certain ways. We have to kind of build on what we know from before. So I know that whole numbers work this way, and that is exactly what this would be. So therefore, this is true. You can do the similar thing for associativity. So I'll let you off the hook there. You can do a similar thing for this guy. This is where the parentheses move, right? Okay. And then the final thing is identity. What would the additive identity be for fractions?
Still under addition?
Yeah, additive identity.
Plus 0?
It's 0. I love it. So, and the beautiful thing about 0, so if I have A over B and I want to add 0, how do I make the B on the bottom? I multiply by B. 0 times B is still freaking 0. All right.
What?
Stop for a minute. So when I just write a number, when I just write 7, like we said a minute ago, what's underneath the 7?
1.
1. So when I just write 0, there's a 1 underneath.
Oh.
How do I make it into a like denominator where the denominator is B? Multiply top and bottom by B. The top is still 0 because 0 times anything is 0. And then, of course, this is this, and then this. These are whole numbers. So we already know that the additive identity leaves this alone. So sure enough, 0 is still the additive identity because it doesn't change the fraction. Okay. And again, I know we know this. We should know this. You knew it was going to be 0. Okay. Yeah, let's do one more thing here. And I'll show you some videos. Yeah, how about, all right. We talked about mixed numbers a little bit already. So just a real quick review. How do I write 15/7 as a mixed number?
2, 1, 7.
Yeah, 7 goes into 15 twice with 1 left over, right? I like it. Just to remind you guys, we did the funky little thing the last time where we took 15/7 and we made it 14 plus 1 over 7. There's 2. There's 1/7. Okay, I like it. So what about this? Yeah, sure. I'll make it nice. That's just gonna be what?
5 and 5, 6.
5 and 5, 6, 11. Now, that one was easy because it was like denominators already. Mixed numbers, I want you to realize, we already understand something like, what would this be? What's 1.1 plus 0.7?
1.8.
Holy shit. And do you see how this is what would be called like a mixed number? Because then they have a whole part and a decimal part, which a decimal is just another name for an out of tens, right? Out of some multiple of tens. So 0.1 is a fraction, just written in our base 10 system. Okay, so those are gonna get freaky in a minute. In fact, let me throw this one at you, let me see. Let me see, I think we got a nifty example already. Yeah. How would I do this? And it's gonna be something like, let me see, how do I show this?
Should we change them to improper fractions first, or just keep them like that?
I wanna keep it like this.
Okay.
6 and 1/5.
Yeah, so there's two ways you can do this. One way is just to do it directly and sort of be illegal for a minute, right? 3 plus 2 is 5. 4/5 plus 2/5 is 6/5, right?
Yeah.
Now why is that no good?
Because the numerator is bigger than the denominator.
Yeah, so I want you to realize, the weird thing about that is, it's sort of like somebody trying to shove the number 11 into a single place. So it's kind of like, this should have rolled over. Because every time I get a full 5/5, it should roll over, right? Is exactly what happens. So take 5/5 away, make this a whole other 1, and then I got an extra 5th. Now another way to do this real quick, sort of like that mental math we did before with the compensation. You guys remember that word? Okay. Or even, what was the other one? Compatible numbers, if I remember correctly. Watch what I can do. Look what I can do. 3 and 4/5. I can steal a 5th away from that guy. So now this is 3 and 5/5, which is 4, which is still 6 and 1/5. Okay. You know, so a lot of those old, what do you call them? Strategies for adding numbers kind of carry over, because fractions are made of whole numbers, so the strategies should carry over. Okay, all right. Oh yeah, one last thing. And then we'll look at the videos. What if I wanted to do, so I don't think this is what they called it before, but we call it a range estimate for fractions. Do you remember when we did it was 870 times 650, and we did 900 times 700, or 800 times 600? We got that range?
We had a range, kind of, not a range estimate, just an estimate on the test about decimal stuff.
Yeah. So if I had 4 and 2 11ths plus 15 and 3 7ths, how do you think I do a range estimate for what that is? It's between what and what? What would you think? What would you think? Sure. What would you think? So how did we do it with
21.
how did we do it with this? Didn't we ignore this shit and say 800 times 600 down, and then 900 times 700 up, right? When we do the same shit here, ignore this shit. 4 and 15 is
19.
19. And then I can think of 5 plus, so up,
20. Oh.
Up, both.
21.
19 to 21. So the answer to this is somewhere between 19 and 21. All right, that's the very, very kind of base level. It's just ignore the fractions completely. It's just something, 4 and something and 15 and something. Well, it's between 19 and 21.
How
Yes.
did you get 5 plus 16?
All right, so let me make this. So range estimate means take them both down to whole numbers, right?
Uh-huh.
So it's the answer is definitely more than 19, yes?
Yes.
Because this is more than 4 and this is more than 15.
Yeah.
And it's definitely less than 5 plus 16.
Oh.
So it's between 19 and 21.
Okay.
I like it. And that's really exactly what we did before, to do that between stuff. I like it. All right. So let me shut up and let me show you the videos of a few things, and then we'll do some manipulatives. Yeah, I like it. You guys ready?
Yep.
Good. I was gonna say, I thought I had you figured out. So just got a couple of videos, I think, yeah. Yeah, okay, we'll do this one. Okay. This is everybody's memory of this class is Panasonic. Oh, there's my little manipulatives.
So first of all, can you read that?
1/2 and 1/4.
What are you gonna do with it?
Add
Okay, can you go ahead and do that, and then talk your way through it, drawing pictures, whatever you'd like to do.
this one is 2. And 8, no, 6. Oh, you have to switch the bar.
And of course, yeah, everybody said that, right? So I kind of like this, he picks up on that.
So you said something about switching the bottom.
Yeah.
What do you mean by switch the bottom? Did you do that, or what did you do to get this?
I just added them.
Okay. What do you mean? Do you think that's the right answer, or you seem a little hesitant?
I don't know. I think you have to switch the bottom, like, so they're both the same.
So, how would you do that? What would you do?
So that could go to 4.
Okay.
Times it by 2. And then you have to times the top by 2.
Okay.
2, and then that's 2. And that's. And you can add them.
So which one do you think is right? The 3/4 or the 2/6?
3/4.
Okay. Why does 2/6? What did you do to do the 2/6? Get the
I just
2/6?
added them. Because there was 1/2 and 1/4.
Okay, so you just added the numerators, the top number, and added the bottom number.
Yeah.
Okay. Okay. Thank you.
Now, I'm curious, I mean, I always kind of was like, why doesn't he go a little further with, because the student obviously understood there was more to it, right? But he sort of followed through that first thing he was saying, sort of because it's sometimes hard to let go of your first approach to something. But we're gonna see with manipulatives here in a minute how that would be really obviously wrong. There's a really cool thing, I know I'm going back and forth, but you got, I sort of forgot even was there. What's really weird, it's never correct to add two fractions together like that. Where am I? But if you do add these together, I'm gonna put an arrow because it's wrong. 2/6, which is 1/3, correct? If you ever do that, every time you do that, the answer you get is between the two original fractions. Are you guys understand? Isn't 1/3 between 1/2 and 1/4? Yeah. 1/2 would be halfway, 1/4 would be there, 1/3 would be in there somewhere. Isn't that kind of neat, maybe, a little bit? So if I had to find a fraction between 2/7 and 3/9, let's make that a little more interesting. 3/10. What would the fraction be between those two? What fraction is definitely between those two? So again, how did I get 2/6? I just added across,
17.
which is not the right way to add things, which is why I wouldn't even show this, to be honest, to somebody just learning fractions. Because the minute you show them that this does something, they'll think it's the right thing to do, right? But this does something. It finds a fraction that's between both of the originals. So what fraction is definitely between 2/7 and 3/10?
5/17.
5/17 is between these two, for example. Right. That's just a little funky aside though. Okay. On the heels of that though, let's do this. I do have this neat thing here. Oh, let's see which one. Here, I think it was this one. I think it's this one. We're gonna find out. Okay. So can you guys see that okay? This is kind of nifty. This is really, really basic. Which one of these fractions do I have to change, obviously? In order to add these together, for example, I want to make them have the same denominator.
Change the 1/2.
Change the 1/2. And the visualization is nice. You can see that 1/2 is more than 3/8, for example, right? So if I can chop this into 8 pieces, then these will go together better. I can compare them easier. So let me just go ahead and chop it. Chop, 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 chop. So now you can see that 1/2 is equal to 4/8. Right? So one manipulative you could have are these, they're called Cuisenaire rods. We have some, but nowhere near enough to even do anything with, but that's kind of sucks. But they're just differently, in fact, I do have this. Let me show you what I got. I do have, which one do I want? I want this one. Okay. I do have these. They got a little knocked around. Poor little dudes. Is that too many? Yeah. So for example, there's 10 little tiny cubes here, right? 10 little tiny ones. So the orange one would be a whole 1. And each one of these would be 1/10. Is that cool? These are each 1/10 of the orange dude. So how many tenths is the blue dude, for example? What's it look like? He's how much less than the...
9/10.
Yeah, say again?
9/10.
9/10, exactly. And you can keep going with all the different lengths. I think they go down, so this is 9, 8/10, 7/10, 6/10, 5/10, 4/10, 3/10, 2/10, and of course then you get your little 1/10. So you can imagine you do a decent amount with these things if you had enough of them, which I don't. But that's just one example. So you could do something like, what is 2/10 plus 2/10? Well, that equals to this color, right? I have no idea what that color is. Is that purple?
Purple.
Violet, purple, fuchsia? All right, anyway. So it's sort of like the base 5, the base 3 that we played with before. It's the same idea. It's in fact, I really want you to understand, 10 ones makes a full 10. Ooh. 10 tenths makes a full 1 the same way. So the more you can get students to understand that the decimals have to act, I know we're not in decimals yet, have to act the same way as whole numbers because they're just a continuation of that idea, the better they're going to be with decimals. Okay, so that's for later. Let me show you this. Let's continue with this thing. I think it's this one. So let me put in here, we didn't have to change this. We made this into 4/8. I think it's a little bit cool what it does here. Now watch. So it wants me to drag the x until it's on 3/8. So let's see, 1, 2, 3/8 is right there. That's nice. It tells me oh, thank you. It wants me the same thing. This obviously 4/8 is obviously right there then. Now I'm going to try to find a fraction that's in between 3/8 and 4/8. Let me see if you guys understand what I'm about to do. Yeah, so give me, what's one answer you can get?
3.5/8, but that's not.
I love it.
That's
Well, it'd be 3.5 over 16, to be honest, because you'd have to add and divide by 2 to get in the middle. But what can't we do what we just did over there? 4/10, which is 2/5, right? Hold that thought. Is everybody cool with that? 2/5 has to be between 3/8 and 1/2. Yes? So watch this. I can change how this is sliced. Right now it's 8, a step of 1/8. I can make it a step of 1/5, and look what's right in the middle. 1/5, 2/5. Red fifth, blue fifth. Dr. Thuth. Okay. That's kind of neat. I like this. This is kind of a nifty visual. You could also just sort of blindly start doing this and say, like, there's one that's in the middle. 1, 2, 3/7 is in the middle. And you can just keep going until you go a little insane. 1, 2, 3, 4/9 is in the middle. Anyway.
That's like more middle.
Second?
It's more in the middle.
Oh, I see what you mean. It just has to be somewhere in the middle. It doesn't have to be perfectly in the middle. Yeah. If I wanted to find the number, I think this is what you were just trying to do. That is perfectly in the middle of those two fractions. How do you do it? The number that's perfectly in the middle of those
Divide,
two.
multiply.
Say again?
Divide and multiply by 2 or something. I don't know. You said something. I said 3.5
All
over
right,
8.
here's where you're almost close. To find the middle of any two numbers ever in the whole universe, you add them and divide by 2. Yeah, just take the average, right? Somebody help us out. What is 3/8 plus 1/2? 3/8 plus 1/2.
7/8.
Yeah, because it'd be 3/8 plus 4/8 is 7/8. Divide that by 2 is 7/16. Is that right? 7/16 would be between those two. And let's see if we make it go up to 16. And 7/16 is directly in between those two. There we go.
Yeah.
Yeah. Especially if we move a little purple over a little bit and a little red over a bit. See, it's right in the middle of those two. Yay, 7/16. Okay, maybe. Plus, all right, I know. What really sucks about this, 3/8 and 4/8, in the middle of 3 and 4 is 3.5, which is where you got that. You guys with me? That sucks so bad. So wouldn't it be better if I made this 6/16 and 8/16? And what is directly in the middle of 6/16 and 8/16? 7/16, which we just got, right? Okay, look, okay. So there are a ton, and remember, what's one of the most important things when you're teaching students something kind of new to them is to connect it to something they already understand. They already understand the number line, right? For example, they already understand whole numbers at this point, right? So you want to connect everything you're telling them to something that they already kind of know. All right, so let's do this. Okay. Let's see, how much time have I left myself for this? Not much. How many people do I have? 2, 4, 6, 8, 10. Of course, I got an odd number. This is the way it's going to be. I need you to pair up and maybe one group of 3, right? All right. Can everybody else pair up? I know if you dislike working with other people, I'm very sorry. You guys are pairing? Who else is a pair? Let me see who else needs.
Wait. Do you have?
Yeah, there you go. You guys, I think it's everybody. Luis, you and Emma are working together, right? Alright, so these are the shapes that we dealt with before. Real quick, we did it on the computer, and we saw how they were clicking together on the computer. Just remind me, can you take one of each shape out, or just dump them all out? I think you guys, that's what I would have done. Dump them all out. And then, kind of wish that we had larger desks. Wouldn't that be nice? Or like tables would be good. All right, let me see if I have enough stuff for myself. Oh yeah, I got these big fat ones here. I love these. Look at that. Wow. All right. So let's all remember how this stuff works. This is a whole 1. Yes. So then what's a half? Second?
Trapezoid.
Yes, the trapezoid. The red one is a half. I like it. And then what are these guys?
2/4 of it, or
No?
1/3.
1/3. I like it. Because again, how would you show students that's true? You would say you need 3 of them to create 1 whole. So each one of these is 1/3. I like it. Okay. What else we got? And then these guys, of course, 1/6. And you can even do it like this. Aren't they 1/2 of 1/3?
Yes.
That's 1/2 times 1/3 is 1/6. I love it. Now, can you please represent for me? Ooh. Let me turn that one off again. Represent for me 3 and 1/2. Right? 3 and 1/2. So everybody got 3 and 1/2 represented?
Yeah.
I like it. Okay. And now I want you to add to that 2/3. Now, how would you do this?
Oh shit, we're missing. Boom. Right. So you have two of these. So we make a whole.
Like that's all right.
So 4
So I want you to play with the shapes you've got so you can get a nice complete answer. Right? And of course we know how fractions work. If you bring a little bit of that thought in, a little hint would be, what's the LCD? 6. So can't you break down your blue and red pieces into 6ths? Yes? So watch. So of course this is our first foray, and I'm kind of like throwing you out on your own. Can't I replace this red one with 3 triangles?
Yes.
Yes? So that's the same thing I just had. Bam. And can't I replace each of these with 2? Let me see if I even have enough. Yes. You can do it. There we go. Alright, so now I've got, they're just green, they're not red and blue anymore, but that's what I just had, yes?
So when we have to do the same one for the yellows now?
No. Because, is
Colorado.
everybody with me?
Me too.
Yeah.
So I got the same shape as the trapezoid. It's just green now, right? And I've got the same shapes as what's called rhombi, but we're gonna call them kites maybe, or diamonds, right? Now what can I do? This is just like that base 5, base 3 kind of stuff we did. Can I make a complete yellow shape?
Yeah.
Yeah. So then I can replace that with the yellow.
Am I gone or what?
So then what's the answer?
4 and 6.
What's the answer?
4 and 1/6.
4 and 1/6, yeah. Of course, I just missed all that. It's too bad. But if I do this, all right, we should all be able to do this. 1/2 is how many sixths? 3. 2/3 is 4/6, right? We could do it either way that we just did it earlier. We could do 3 and 7/6. And then we can realize that 6/6 is a whole. So we get 4 and 1/6. But there it is visually, right? So the more students do this, and then you sort of start to tie it in with a computational way of doing it, the more intuitive feel they're going to have for how fractions work, right? And this is what I'm always curious about, how the teachers out there right now do this kind of stuff. Do they do enough of this kind of stuff with students? And is this why nobody seems to understand fractions? All right, let's try another one. What about, can you represent, let me see, how many total triangles do you have?
6.
So you guys have 7?
6.
6, yeah. They were the ones that I had like none of. This is as many as I've got. And I got like a stupid amount of other shapes. But so let's do this. How many blue ones do you guys have?
Is it
14?
13.
10.
Dude, 10? Yeah. This is not a equal distribution of resources. This could be a whole sociology class thing. All right, let's do this. Let's do. All right, you can do something as simple as this. What would this be? What is this?
6. 7. Wait. 6.
Now, 6 what?
Half.
Each blue piece is what?
6/3.
Yeah, 6/3. I like it. And of course, what could you have students do with these?
2.
Reorganize it, yeah.
So,
Exactly.
I forgot.
So it should be able to make.
Yeah.
2. Okay. I like it. So then, if you kind of can do this. All right, this is getting a little ahead of where we currently are, but can you guys imagine you could say, what is 2 divided by 6?
What?
So if I say, what's 18 divided by 6? What is it? 3. What's one way of thinking of that? Can I think of it as taking 18 and breaking it into 6 parts? That's sort of like the sharing thing. You got 6 people and got 18 apples. How much does each person get, right? So 18 divided by 6 is 3, right? Because that's what you get when you break it up into 3 parts. 18 divided, yeah. So if I take this, 2 divided by 6, so I break them all up into, how do I say this? I got a little bit ahead of myself. 2 cut into 6 parts. They're each 1/3. All right, so I need to make that connection better. I got a little ahead of myself. Oh, it's good. One that's, let me do this. One that's a little bit easier to think about is, what is like, what's a good thing I can do here? Let's see. Let's do that. Yeah, let's do that. What is 2, say, I think you guys have it up for this. What is 6 times 1/3? I think that's what I was trying to get at, yes. 6 times 1/3. Wouldn't that be 6 of these? 6 times 1/3, and then that would lead you into creating 2 total shapes. So you got, that's 2. What about, so that's 6 times 1/3, because 6 times 1/3 means 6 1/3. What about 1/3 of 6? What would you need to be able to do? So 6 times 1/3 should be the same thing as 1/3 times 6, correct? Because of commutativity. But technically, is 1/3 times 6 manipulation-wise the same thing as 6 times 1/3? No. 6 times 1/3 means 6 1/3 pieces. 1/3 of 6 would mean, and I don't think you can represent this, but there's a nice fountain. 1/3 of 6 would mean you've got 6, and then you cut them into groups of 3, and there's 2 in each. Right, so that would be 1/3 of 6, but either way you do it, you get 2. So it's another way to show commutativity of these things. Let's try another one of these before I get you. Let's do one more of these, I think. What about Can you guys do 1 and 5/6? Oh, let's try some subtraction. 1 and 5/6 minus 2/3. Try to represent 1 and 5/6.
1, and 1, 2, 3, 4, 5, 6. Oh my god. Oh wait, 2.
I think you guys should all have enough. So 1 and 5/6
Oh, that's back. So we trade that and then these two.
minus
And
2/3.
so we got that thing. So 2 and 1/2. Don't play with it.
Now think about it. 1 and 5/6 minus 2/3.
Oh,
It's
oh,
one
we're
and
adding
one
it.
six.
Hey, calm down. Calm down. We didn't see that. What?
No, I appreciate the enthusiasm.
Alright. Yeah, release for the tax law, dude.
Here's 1 and
Hold
5/6.
on.
So there's a few different ways. Yeah. All right. What's one way that somebody did it? What's one way that somebody did it? Anybody want to share? How did you do this? I know you started with this, right?
And then I took the two blue ones and then put them on top.
I like it.
We built the green ones into blue ones and we took them away.
Okay, I like it. So you could replace these
God.
and then just take those away. Sure. I like it. Did anybody do it differently at all?
Oh,
You could say, okay, real quick, last thing, and then we'll head out. You could say, I don't have enough triangles for this. That's what sucks. Yeah, I can't do it that way. The other way to do it is to replace this with green and then kind of take it away, but it's basically the same idea. All right. So next time we're going to do more. We're going to get into the multiplication stuff.
Multiplication.
Finish up chapter 6. Yeah.
We're gonna have more of these.
Don't worry, I'll figure something out. I might have to make bigger groups of people. Yeah.
I want to get away, but I wanna fly.
I haven't heard that song in years.
Thank you. Thank you. Your homework?
Yeah, I was in here last, Tuesday, I was in here last Thursday,
Uh-huh.
so it was my homework that we tried to do in test.
Oh, that, no,
Yeah.
that I grade eventually. Someday.
Okay, no worries.
Yeah.
What did you grade for the time for homework?
what?
Because I remember giving you,
Mine, it was old. It's sticky.
Yeah, you gave me like 5,
5.2.
2.
5.28?
Yeah. So I'm gonna grade that soon.
Okay, cool.
To be honest, I haven't gotten much yet, so I've been sort of focused on other classes.
Ah, gotcha.
Yeah.
Oh,
Sorry I showed up late today. When I was driving from my home, I was almost there to school, but then there was a ramp detour. You know when those.
Oh yeah, I
construction-
know. It happened to me too.
Yeah, and we
Just
had-
no warning.
Yeah, no warning, nothing. So we had to. I had to make a turn all the way to Santiago to get over here.
I understand.
Yeah. Anyways, have a good day, sir.
See you.